think we should start now. So it's a great pleasure to ask Daniel Harlow to give his survey talk titled Recent Progress on the Black Hole Information Problem. Yeah, good. We can see your presentation. You can full screen it probably, and please start. Yeah.
Very good. And everyone can hear me, I hope so.
Yes, yes.
All right. So let me first start by saying thank you for the invitation to speak here. It's an honor. I've always enjoyed my time in India with the strings community. It's a pity that I can't be there in person this time, but hopefully sometime soon. I wasn't exactly sure. So what I was supposed to do with this talk, I tried to put it kind of somewhere in the vicinity of the kind of review talks that are given at the Strings Conference, but maybe with a bit more still of a focus on recent results of my own, just so liven it up a bit for me. So I am happy to take questions throughout the talk. I don't need to wait until the end. So if anything bothers you, feel free to, I guess, type in the chat or raise your hand. And maybe Sunil, if you can look to see if people raise their hands.
Sure, I'll do that.
And I'll try to look at the chat too, but if I somehow miss it, then just, interrupt me, please.
Okay.
Okay. So let's just start with the big picture, since this is a review about the information problem. So combining relativity and quantum mechanics, that's the biggest problem in theoretical physics. Yeah, we still haven't solved it. And by solved it, I mean we haven't succeeded in constructing a realistic theory of quantum gravity. We've constructed many unrealistic theories of quantum gravity, but not yet a realistic one. Unfortunately, I think part of the reason why we haven't succeeded is the lack of experimental data. We do have, sometimes people say there is no data. That is not correct. We certainly do have data. For one thing, we know that gravity exists, but beyond that, we know that black holes exist. We've measured some of their infrared properties. We know the sign and the magnitude of the cosmological constant. We know how many large space-time dimensions there are. We know about the density perturbations in the CMB. I mean, so these are all pieces of information which do give us information about quantum gravity, I would say, at least in some sense. But so far, this kind of thing hasn't been enough for us to identify a unique, consistent theory, or even any theory which is consistent, even just with the data that I mentioned so far. So in some sense, the quantum gravity problem is theory limited, right? Even just the things I'm mentioning here, we don't have a theory that explains all of them, even though we've had this data for a while. Okay, so what do you do if you don't have detailed experimental evidence? Well, the next best thing is you take the theories that you do have and you extrapolate them to extreme regimes where they run into trouble, they become paradoxical or inconsistent. And then you think about what needs to be added to the theory in order to resolve this tension. There's already a chat. Okay. Oh no, that's to Zohar. Okay.
Yeah, that's between Zohar. That's Zohar replying to Ethan.
Okay, so for example, Maxwell thought about capacitors that are charging up really fast, or Einstein thought about trains moving close to the speed of light. And even though we still don't have trains that are moving close to the speed of light, this was a good thing to think about in terms of understanding better the structure of the theory and how it needs to change. In quantum gravity, the most obvious regime where you get into trouble is in high energy scattering, right? So general relativity is a non-normalizable theory. And so if you try to compute even perturbative quantum corrections, right, you can't reliably compute them without further input from short distance, right? You can make up some kind of rule, but what you get out will just be your rule. It won't be something that came from a theory, really. The great accomplishment of string theory, at least historically, was, and supposedly string theory is the subject of this workshop, right? Although I didn't go to all the talks, but I guess not that many of them were about string theory. But anyways, the great success of string theory is that it gives concrete, UV finite, although vacuum dependent predictions for what these quantum corrections should be. Okay. On the other hand, there's actually another regime where if you try to combine gravity and quantum mechanics, you get into trouble. And this one actually may, in some sense, be of greater importance. And this is the regime where you go to finite, but not necessarily large temperature, but then you think about very long times. So in this regime, gravity has long-lived quasi-thermal excitations, very generically, which are, of course, black holes. And thinking about them in this regime, where you're away from large regions of large energy density, strong curvatures, nonetheless, you can get into paradoxical situations. And the most famous of these is the information problem, which is the situation that I'm going to talk about in this review. So, okay. So hopefully you're all familiar with the basic setup of the information problem. So so I've drawn it here in asymptotically flat space. So you collapse a shell of matter, which I've taken to be null for simplicity here, to create a black hole, and here's its horizon. And then you think about what the state of the system looks like as time evolves on Cauchy slices like this one, sometimes called nice slices. And so because of the vacuum entanglement between modes on either side of this horizon, for example, these two blue modes are entangled with each other, and these two red modes are entangled with each other, and then this keeps going down the chain and also deep into the UV right near the horizon here. So because of this vacuum entanglement, it causes the black hole to radiate, right? This is Hawking's famous calculation. So these exterior modes, they have some probability for making it out to infinity. And this causes the black hole to lose energy, which, that by itself, okay, maybe it's not so bad. But then the real problem is that if you look at this picture, right, the information about how the black hole was made, like in this infalling shell, is way in here, very far inside on the Cauchy slice. There's, at least if you believe in sort of any sense of locality, it seems like there's no way for the information way in here on this Cauchy slice to somehow get out into this radiation. You could hope that by the time the black hole reaches Planckian size, well, then maybe this radiation and that in some vague sense are not so far away, although actually I would say they still are far away. Then the black hole, by the time the black hole is Planckian size, it doesn't have very much energy. And so if you think it's just going to, radiate into some reasonable number of particles afterwards, there's just no way that radiation that it produces will have enough information to take out to tell us how the black hole was formed. So there are three standard options for how we're supposed to respond to this observation of Hawking, right? These are the three classic options. So option number one is remnants, where you just say, okay, the evaporation stops when the black hole is a mass which is of order n Planck. But this is bad because in a remnant scenario, the entropy of a black hole is not really equal to the area over 4G. And so then the apparent success of black hole thermodynamics in a remnant scenario is just a coincidence. It's an accident. The black hole behaves as if it had an entropy A over 4G, but actually it doesn't. Okay, and so that's not very satisfying, at least to me. Option number two is information loss. So then you say, okay, the evaporation goes all the way. It doesn't stop with a remnant. But then so as a result, most of the information just doesn't make it into the radiation. It's mostly just in this baby universe that is created. So in this scenario, usually the nicest way to think about it is this kind of piece of the Cauchy slice here, when the black hole finally finishes evaporating, that just kind of finds its way off into some closed universe that no longer talks to our universe, and that's where the information is from now on. So that actually doesn't bother me so much if the information goes into a baby universe. I mean, sometimes people say, oh my God, that means that the exterior S matrix is not unitary, but I mean, who cares, right? I mean, there's still unitarity. It's just that you mix with the baby universe. So I think saying S stagger S is not equal to 1 maybe is not such a big deal. Actually, what bothers me more about this scenario is that it again implies that S is not equal to A over 4G, because when the black hole, just before it finishes evaporating, right, it's basically the same as a remnant. You have some object which is storing much more information than A over 4G. And if you could throw, for example, that into another black hole, and that would give you a black hole where S is not equal to A over 4G. And so to me, that's much worse than having the information go into a baby universe. And then finally, there's the option of unitarity, which says that the evaporation goes all the way, but actually now the information makes it out into the radiation. And so that can be consistent with S equals A over 4G, which we like. But there seems to be some apparent tension with the smoothness of the horizon, which is sometimes called firewalls. And whether you believe that or not, in any event, if this option is going to have any hope of working, it really requires massive non-locality in order for the information in the interior to make it all the way out. And I emphasize that in order for it to make it all the way out, it can't just make it out at the end, right? It has to at some point start coming out earlier. So that's something that Samir Mathur, I think, explained very well. So let me review a bit his picture of this, right? So most days people go for the third option. But I think a lot of the people who go for it don't really appreciate how radical it is. So for example, sometimes you hear people saying things like, well, anytime you have a bunch of corrections of order e to the minus s, and you have a lot of them, so then you get to multiply by e to the plus s, and then, why should you believe anything that Hawking said? Okay, that's kind of a phenomenologist point of view on the information problem, if you like. But as Samir explained, I think very clearly, this is not a good argument, right? Like, there's not a sense in which a small correction to Hawking's story can restore unitarity. And the easiest way to understand this is by using this page curve, where you plot the von Neumann entropy of the radiation as a function of time. So I put a star here in case Suvrod is here. I'm not sure if he's actually here, but anyways, I'll just comment. So when I say the radiation, I mean the radiation. I don't mean the holographic description of everything that lives at spatial infinity, right? I mean, I don't expect to obey a curve like this, but I'm talking about the radiation that is actually in the space that you go around and measure with beam splitters and photons, and mirrors and so on. And so if you look at the von Neumann entropy of the real radiation, right, then Hawking predicts that it will just go up, 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 up until the black hole evaporates, and then it'll saturate at some finite value, whereas Page argued that by unitarity, since the state has to be pure in the end, the curve has to turn over and go back down. So unitarity changes the slope of this curve at order 1, not at order e to the minus s. That's really the point that Samir was making. And so if you want to change this story, you have to somehow explain why this curve turns over here. Just kind of mumbling about e to the minus s corrections is not going to do it for you. So for this reason, a reliable calculation of this page curve has been viewed as one of the major requirements for a satisfactory resolution of the information problem. I won't say that just having this computation solves the problem. I think that's not true, and we'll talk about that more as we go on, but it's clearly major progress. And in fact, this was done right a few years ago, which came as a surprise, I think, to many people, especially people who weren't paying attention. But you can indeed do this calculation. And so there were these groundbreaking papers in 2019 by Pennington and then by Almeri, Engelhardt, Merrill, Maxfield, which explained how to do this, which was really an advance. It's one of those things that in retrospect, as maybe we'll see it's kind of obvious that that this was possible and should have worked, but everything is obvious in retrospect, right? I mean, at the time, this was a very daring thing for them to attempt, and it was amazing that it worked. So the main input to this calculation is the quantum extremal surface formula, which was introduced by Engelhardt and Wall in 2014, which is basically just, at least in the way they were thinking about it, it's a refined version of Ru and Takinaga's formula for computing the von Neumann entropy of a spatial subregion in a holographic CFT. So the justification for this formula, right? So this formula is really the workhorse of this page curve calculation. And so we're going to spend most of the rest of the talk talking about this quantum extremal surface formula, right? So the justification for it rests on some tripod of quantum information theory, Euclidean gravity, and semi-classical intuition. I think I meant to change semi-classical intuition to holography, and then I forgot. Okay, but either one is true. And actually, the subject has grown so large that already any systematic review is impossible. So I'll instead just kind of give you my view of how the logic goes. I'll try to condense it down to something which maybe is not necessarily how things were originally said, but maybe how they should be understood now. And I'll also talk about some new results in the end. So that's it for the introduction. Let me pause and ask if there are any questions or comments. I'm surprised I made it this far, actually. Everybody's happy?
Yeah, I think so.
Okay, yeah, I think I don't see any raised hands, so, okay. All right, I apologize if my son contributes to the talk in the background. He's a very enthusiastic 3-year-old. Okay, so then let's go on to this quantum extremal surface formula. So let's just recall a little bit what the formula looks like. So here I'll present it first just in ADS CFT. The idea is if you have some boundary subregion. So here I've drawn ADS3 CFT2 just because that's the limit of my drawing abilities. If you have some boundary region R, which here is just this circle half interval here, or a circle interval. In an interval, it's half of a circle. That's what I should say. Then there's a formula for, at least if you have a state of the dual CFT where the bulk description is somewhat reasonable, then you're supposed to use this formula here to compute its von Neumann entropy. So what does this formula say? Let's try to unpack it a little bit. So the idea is we look at the set of all codimension 2 surfaces in the bulk, which are homologous to R. So like this XR here is a candidate surface that's homologous to R. Okay. Just to show that although I was trained on the west coast of the US, I know what homologous means. It means that there's R of X here, and then there's a minus sign here. Okay, so the boundary of, there's some spatial region R of X, which I've drawn kind of in between here. It's behind this other stuff that I'll explain in a sec. And then the boundary of this kind of piece of the bulk Cauchy slice is R minus XR. Okay, that's what it means to be homologous. And then the domain of dependence of this homology surface is called the entanglement wedge. But let's finish going through the formula first. Okay, so we consider the set of XRs, which are homologous to R. And then among that set, we extremize this quantity here, which is the area of XR over 4G, plus the entropy of bulk fields living on this homology surface, R of XR. Okay. So then first we extremize that over XR. So we are only interested in XRs where this thing, which is called the generalized entropy, is extremal. That's why we have the name quantum extremal surface. And then if there's more than one such quantum extremal surface, then we take the one which also has minimal generalized entropy. And then if there's a tie for the minimal ones, then we don't care because it gives the same answer for the entropy. And so finally, just for future reference, this domain of dependence indeed is called the entanglement wedge of R. Okay. So hopefully this kind of picture you've seen before. In general, the domain of dependence, for example, the null geodesics can focus and make a seam. That's what I tried to draw here to just make it a little more generic. Now, if you're given a formula for entropy in a microscopic theory of quantum gravity, like ADS-CFT, it's natural to ask if you can use it to compute the page curve. Surely some people, asked that immediately after Rune Takenagi proposed the first version of this formula. However, there are a few obstacles which prevented the calculation from happening until recently. So the first one is that, big black holes in ADS don't evaporate. And if you want to talk about the page curve, at least in the usual sense, you need a black hole that evaporates. But we don't understand the duality well enough to trace the evaporation of a small black hole in the dual CFT. So we can certainly, in principle, set up the information problem in ADS by just collapsing a shell of matter to form a small black hole and then waiting for it to evaporate. But yeah, good luck following that in the dual CFT.
Daniel, I think Shiraz has a question.
Oh, okay, sure. Please go ahead, Shiraz.
Hi, Daniel. In the term which said matter on your previous transparency, you had a piece which was S bulk. Does that include the entropy of gravitons?
Yeah, it's supposed to, although I don't claim that the community has fully understood the systematics of that.
Could it be that when you understand that very well, we would need to include some sort of path integral over the entanglement entropy surface as well?
Well, in perturbation theory, that doesn't seem to be true. There's some, I mean, to deal with that, you basically have to fix a gauge. Is one, at least the most obvious way of dealing with it, although not probably the most pleasant way of dealing with it in the end. One could hope that somehow properly doing that would introduce this area term as well. I guess that's what you're trying to get at.
Yeah, I just the feeling that if you're extremizing something in a classical limit, feels natural to sort of let it fluctuate away from classicality.
Well, yeah. So I mean, there is a there is a understanding of this as coming from a saddle point approximation to a path integral, but actually, which is due to Lukowitz and Malesana. I'll talk about it later. But in that approach, actually, the gravitons are still more of an annoyance than something rather than something essential. Yeah, because So in that, right, I mean, in that story, there is a way of phrasing it where there's some integral over the surface, and then you extremize and get this. Yeah, but you in some sense you have that even before you think about the gravitons.
Okay, so away from in the large end limit, apart from the S bulk, should we also be integrating over some fluctuations of the surface? I suppose. Should we?
No. Yeah, no. There's no. We don't think that there's like some brain action or something on the surface, right? Yeah, I mean, it's just how shall I say? No, I mean, this formula is supposed to be like, to all orders in perturbation theory, there's a particular surface that wins this computation, right? Because in the end, you will just want to get a number for the entropy. So you don't want it to be like, if H bar is finite, now the entropy is the expectation value of something, right?
Okay, thank you.
Yeah. Okay. Okay. So problems with other questions? I'm happy to do more. I'm not in a big rush.
Yeah, I have a question. Like usually quantum corrections lead to log terms in the entropy. So why aren't such terms there here?
Yeah, that's so okay. I'm not actually sure. I think it's possible that the graviton loops do lead to logarithmic terms in this formula. It's something that a few people thought about, but I think nobody has come up with a systematic understanding of that yet. Yeah, but I'm certainly, I mean, it's certainly possible. Yeah, the set of people who understand the logarithmic corrections to entropy is kind of orthogonal to the set of people who understand this formula, but hopefully that'll change. I mean, I guess there are people of both kinds in India, right? So.
Okay.
Yeah. I mean, maybe I'll just make one comment, which is that usually those terms are like temperature independent, I guess. So, which somehow seem less important for page curve type calculations, but there's just some vague comment. I mean, it's still certainly important to sort that out. Any other questions? Okay. So we were talking about problems with trying to compute the page curve using the QES formula. So one was that big black holes don't evaporate. Another problem was that until recently, this formula, the quantum extremal surface formula, was just understood as describing perturbative corrections to the classical Rutakinagi or Hubei-Ragamani Takeyanagi formula. So like in this formula here, right, we understood this term as being order 1/g, these corrections as being smaller, and then we understood this term as being order g to the 0. Okay. So then if this term is the dominant term and this term is small, then this quantum extremal surface should be close to some surface that just extremizes A, right? That's what you would expect, which we call a classical extremal surface. But there's just no classical extremal surface around in the page curve discussion that that would have the right properties to do what we want. And so then, naively you just say, okay, so why would including perturbative corrections help? And so, for example, like I was in the camp that thought this, although I didn't think about it that hard, apparently. So the first of these problems, right, you can solve it by coupling the dual CFT to a non-gravitational reservoir, and then that allows big black holes in the dual CFT to evaporate. And so that was one of the steps. That idea actually had occurred earlier to some guy whose name I don't remember, who was a student at Pachinski. He wrote a paper about it maybe 10 or 12 years ago, maybe 15 years ago now. But he didn't know about the quantum extremal surface formula, so it didn't help him very much. But then if you try to play this game of coupling the dual CFT to a non-gravitational reservoir, then there's a third problem, which is that, well, okay, so far this QES formula, right, it was proposed as giving von Neumann entropy of the CFT subregion, but then, okay, so are we allowed to use it for a non-holographic system like this reservoir that we coupled to? And if not, then how are we supposed to compute the page curve? Okay. And so these are kind of all the issues that had to be overcome, right? So the great insight of these 2019 papers of Pennington, Almeri, Engelhardt, Merrill, and Maxfield, although this is not necessarily quite how they would have phrased it, is that the second of these arguments is wrong, right? That it's not actually true that a quantum extremal surface needs to be near a classical extremal surface. If you include the bulk entropy term in the QES formula, then actually it can give rise to new quantum extremal surfaces, which are far from any surface of extremal area. Jorge Roja, that's correct. Yes, thank you, Amitabh. Has put the name of the author in the chat. I apologize for not remembering it. I should have cited it. So let me just explain how this works. First, for the situation where you have, so now here, so this will take, we're going to spend a bunch of time on this. So I apologize. There's a bunch of text and a complicated picture. So here's how the new quantum extremal surface works in the situation where, so if you think about the dashed line in the red dot here, that's the microscopic description of what's going on. So I have a holographic CFT, which I'll call S. Here it is sitting there. And it's coupled to a reservoir R, which has some time slice like this. And so the dimensionality of the reservoir is the same as the bulk description of the gravity theory. Okay. And then the idea is I have some black hole in here, which is since this dual CFT is coupled to the reservoir, then radiation that's produced, so the black hole horizon is over here, and radiation that's produced by the black hole can actually leak out into this reservoir system from the gravity point of view. So for example, this Hawking mode here, which is out in the radiation, it came from somewhere down here outside of the picture, and then it was entangled with some mode, which I squeezed over here so I could fit it into the picture, this one. And this one is in the interior of the black hole. Okay, so that's kind of Hawking's picture of the evaporation. It's the same picture I drew before, except now we're interpreting this line here as the kind of joining between the reservoir system and then the dual CFT, which is then dual, really they're both, the union of the two is dual to this picture of the gravity region over here. Okay. So let's think about the entropy. So to avoid this issue of how do we think about the entropy of the reservoir, let's first think about the entropy of the holographic CFT. Okay, so then we can just use straight up quantum extremal surface, no funny business. Okay. So let's think about what the quantum extremal surface is. Well, at early times, say right after we collapse we collapse some matter, it's just right over here to make the black hole, then the natural quantum extremal surface for the, if we take the whole CFT boundary is just the empty set, right? So the CFT boundary, let's say it's a sphere, right? So the empty set is homologous to it, of course, because I can just take this Cauchy slice here to be the homology hypersurface. And then the entanglement wedge of that quantum extremal surface is just this shaded red region here, meaning that the entanglement wedge of the CFT contains everything in the bulk, at least inside of these null boundaries here. And in particular, it contains this interior Hawking mode. Okay. And so as the evaporation proceeds, you get more and more of these interior Hawking modes. And so as a result, the quantum extremal surface formula via the bulk entropy contribution says that the entropy of the CFT is increasing, which is what you expect, right? Because it's interacting with the radiation. Maybe they started out not very entangled, but then because of the coupling between them, they're getting more and more entangled as the radiation from this CFT kind of goes out, propagates out in the bath system. So that's just the usual story, right? The quantum extremal surface is the empty set, so there's no area term, and you just get the bulk entropy here contributing in the QAS formula. But eventually that entropy becomes so big that you actually win by switching to a different quantum extremal surface. So this is the new quantum extremal surface over here, the one that's not near a classical extremal surface. And then the advantage of switching here is now so now there's a lot of modes out here in the radiation that are entangled with a lot of modes over here. And so if I had used this quantum extremal surface, then all these interior modes would give a big contribution to the bulk entropy term. But if I take this small one here instead, then the bulk entropy contribution to this is small because it no longer includes these modes here and these modes there. But then the price we pay is that now this surface has a finite area, right? And so that area comes with the A over G, which is very big. So at early times, it's not worth it to pay the price to include this. But at late times, it's worth paying the price because even though that area is big, it's smaller than the entanglement of all these interior modes with the radiation. And in fact, that you get into that problem, right at the so-called page time, which is where you expect the page curve to turn over. And so once this situation takes over, then now that you have this new quantum extremal surface XS, and this XS, it's close to the black hole horizon. And so that gives you something that as the black hole evaporates, it decreases with time, and that gives you the page curve that's going down. And so that's really the essence of what happened here, was finding this quantum extremal surface. People will say that there's lots of other things that were important, and I'll talk about the other things later. Okay, but this was the new ingredient, was finding this quantum extremal surface. Everything else just happened, within a few months, right? This was the thing that was the bottleneck for progress. And so, that's why I would say these papers are really the papers that push this. Everything else is in some sense follow-up. In particular, you notice here, I didn't say anything about, islands or replica wormholes or whatever, right? That's all important, but that's kind of secondary. Here, you can see everything without any of that. Okay, now I just want to comment, right? So what happened to this perturbative argument that it couldn't be near a classical extremal surface? Well, that it had to be near a classical extremal surface. Well, what happened, although you have to do the calculation to see it, is that you really balance the 1 over G in the area term. So if we look back at the quantum extremal surface formula, right? So to find an extremal surface, I compute the variation of these two terms. And naively, this term has a 1 over G and this term doesn't. So this term determines the location of the extremal surface. But actually, there's a short distance singularity in this bulk entropy. If you have an entropy of a region and you make the region small, then that creates a divergence. And then when you compute the variation, so in 1 + 1 dimensions, which is the relevant dimensionality for doing this, it's a logarithmic divergence. And so when you compute the variation, you get a 1 over R here, and you can balance that short distance singularity against the 1 over G. And that's how you find this quantum extremal surface that's far from a classical one. Okay. And so daring to do that was kind of the main new input of these papers, while daring to do it and then finding that indeed it works. Okay, so let me pause now again and ask for questions before I go on to talk about the entropy of the radiation. I don't know, maybe everyone's already an expert on all this.
Hi, Daniel, I had a question. So
yes.
So when the two terms balance each other, in the formula, you have the other quantum corrections, right, coming from quantum gravity, which, so when these two terms balance each other, is there a good argument why those subleading quantum corrections do not?
Right. So this bothered me a lot, right? So like, for example, there's the ... here. What about that, right? So, you know, if we, yeah, exactly. I mean, and so that is why nobody did this sooner, right? Is because there was just this intuition that this is a this should be understood perturbatively, and you know, so then you're not allowed to balance the terms against each other, right? But what was appreciated was that although there are higher order quantum corrections, they all go into this ... and those corrections are all extensive. They're all the integral of something local on the quantum extremal surface, okay?
Mhm.
So even though you include those, you can include all those if you want to, but they're not going to help you balance against the short distance singularity here, because none of those are going to produce this logarithmic divergence. So it's kind of a kinematic argument. The S bulk term is special. It's the only term that's able to produce a logarithmic divergence. And so I'm allowed to balance it against the leading term over here, even without worrying about the other terms. Does that make sense?
Yeah. But my one question was that when it's minimized at the extremal point, I mean, even there, I mean, these wall terms do not matter. I mean, you know, when these two terms are separate. Yeah.
Well, so actually, yeah. So I mean, so this bulk term is important for finding the entropy, but it's actually not important for evaluating the generalized entropy. That's in the interest dominated by the area term.
Okay, thanks. Yeah.
Sure.
Sorry, is this a dimension dependent statement that this cancellation or this balancing happens?
No, it's actually not, because although what I said sounded two-dimensional, you know, the information problem really is two-dimensional. You're kind of reducing everything to the sphere, on the sphere. So the two-dimensional scaling is always the right one.
Okay.
You know, because the black hole horizon is always just Rindler, right? Okay, anyone else?
Could there be quantum corrections to the the action term as well? The
S bulk?
action, S bulk, yeah.
I mean, in principle, yes. Somehow, you know, I mean, this is already a quantum thing, right? It's so the way this is usually understood is this is S bulk to all orders in perturbation theory. So somehow
But
by definition there aren't.
Summing over all loops.
Yes. Yeah. I mean, so let me be clear, like this is supposed to be, this is only perturbative in G Newton. It's not perturbative in like, you know, the QCD scale or something else, right? Like, so there could be strongly interacting matter fields, and this is supposed to still be true. It's only important that gravity is weakly interacting.
So what is the form of S bulk usually?
Well, I don't. It's minus trace of rho log rho. Yeah.
And that is supposed to sum over all perturbative corrections.
Well, certainly, yeah. That's. I mean, yeah. Like the entropy of the vacuum for a region in the quantum field theory is certainly going to depend on whether it's interacting or free. I mean, it depends on many aspects of the theory.
No, rho log rho. I mean, trace rho log rho is.
Well, yeah, because rho will depend, right? Because the state rho will depend on the interactions, right? Like, for example, it could be the vacuum. We certainly think the vacuum in quantum field theory depends on the couplings.
So what is the form of rho?
Well, that's it's the state we're interested in, right? I mean, this formula is supposed to work for a broad family of CFT states. You know, it depends on, you know, it probably won't work for states which are so non-semi-classical that there's just some huge black hole that ate everything. But at least for ones where there's some geometry like this, it should be true. And then you just use the bulk state, which is dual to that. You know, including quantum fluctuations and so on.
Okay.
Yeah, something. Did you say the extremal surface changes because of the divergent terms from the S bulk?
Well, it's not the divergent terms. It's that this function is divergent if you make the region small. So it gets big. So it's not like a boundary counter term that we use. It's the part of the entropy which has a logarithm. So that's not something you can remove by adding boundary counter terms.
Okay, thanks.
Yeah.
Subramanya, you had a question?
Yeah. Hi. So I have a naive question. So this adding this extra a non-gravitational reservoir, how should I think of it from the bulk point of view? Like, let's say some part of the ADS CFT dictionary, like the partition function in ADS is equal to the one in CFT. If I have to state something like that, then this
So roughly speaking, I mean, in detail, this has only been worked out in a few cases, but roughly speaking, what you would expect is that, you have some low dimension single trace operators here, okay? And in the bulk, there's some weakly interacting matter fields. And so I can just take those matter fields to be simple without gravity and put them here, and then introduce some sort of single trace coupling here that talks to the boundary conditions of these matter fields. So you could try to do that like in the microscopic description, right? And then this is kind of what the dual of that should look like. There might be a little bit of sort of energy density or something right around the gluing, which I would say needs to be understood better than it's understood now. But I think it's pretty plausible that this is what it'll look like.
Okay, thanks.
Okay, so maybe I'll go on. So that was the story for the page curve where you compute the entropy of the black hole. Okay, it goes up here because there are more and more of these modes in here in the entanglement wedge of S, so they contribute to the generalized entropy. But eventually, there's so many modes there that you need to switch to this quantum extremal surface, which now doesn't include the modes, but then you now have a big area term, and then that area curve term goes down as the black hole evaporates. Okay. Now, once we understand the rules for computing the page curve for the CFT S, then it's pretty easy to guess what the rule has to be for the reservoir. You just take the complement of everything I said here, right? So in this picture, the entanglement wedge of S was this, so then its causal complement is like this. So at early times, the entanglement wedge of the radiation is just the obvious thing. You just take this time slice of the radiation and take its domain of dependence. But then the novelty is that at late times, if you take the complement of this and the causal complement of this entanglement wedge on this Cauchy slice, then you end up with an entanglement wedge of the radiation that looks like this. And so now it has the obvious part, but it's also got this new island region in here, right? And you can kind of tell the same story as before. So over here, right, the entropy is going up because there are more and more of these Hawking modes getting in here. And eventually there are too many, and then you win by including their interior partners over here as part of the entanglement wedge, so that since now they're pure, they give a zero contribution or a small contribution to the bulk entropy. But then you pay the price of now it's this surface that you included, you again have to include its area. And so that gives a page curve for the radiation that also goes up and down. Yeah, so this is what I said. So at early times, the reservoir has the obvious entanglement wedge, but at late times it includes this island. Now, it may seem strange, actually to me it doesn't, but to a lot of people it apparently seems strange to include part of the gravitational region in the entanglement wedge of the reservoir. So below I'm going to talk about some information theoretic understanding of the QES formula, where in terms of that it's basically obvious, but an argument I can already say is that in the end, there isn't really a sharp description between a holographic distinction between, holographic CFT and some other weakly interacting quantum field theory. Just one moment, if there's a question. And indeed, if you think about sort of tensor network models, which are one of the few tools we have to kind of understand these things from a Hamiltonian point of view, it's clear that there's no difference between these. From the point of view of the QES formula, if it's going to make any sense at all, you're going to have to include this island here. So I'll say some more soon about how to justify this, but some people say that in the original papers they weren't justified in including this, but I don't think this is right. I think they were quite justified, especially in Pennington's paper. He knew about some of these information theoretic examples, and it was obvious that from those examples that it was correct to include this. Okay, so that's the story for the entropy of the radiation. So that's it for my review of the page curve calculations. I'll just give people one more chance to ask questions. Then I'll go on to sort of talking about what it means. Okay, I guess we just had a bunch of questions. Maybe I see one. Is there a question? Karen Fernandez?
Yeah, Karen, go ahead.
Yeah, I have one. So maybe I missed this, but is there a the coupling of the ADS with the reservoir. Are there some universal features about this, depending on the black hole spacetime in question that we're trying to emulate in this case? I mean, is the coupling allowed to be generic, and does the page curve depend on the form of the coupling?
Well, you probably don't want it to be generic because you want it to couple the weakly interacting fields in R to the low dimension operators in the dual CFT. So you probably don't want to just add some like huge crud that mixes all that up, right?
So then are there any constraints on the form of the coupling?
Well, there's the one I just said, I guess. Yeah, it should.
That's about just, it. It should not.
Yeah, but I think that's kind of probably. I mean, I would guess pretty much anything that just pick even just pick one single trace field, and just have a direct local coupling to the boundary values of one field out here. Okay, I feel like that would already work.
Okay, thank you.
Yeah. I mean, I should say that this, it would be nice to, I mean, in 1+1 dimensions, people understand this a little better. In higher dimensions, it's something that could stand to be understood better, I would say.
Okay, maybe a quick follow-up. There are these pictures about near ADS2 geometries around the black hole. Could this picture be fit into that in some sense? Has it been done so far?
Well, that's certain. I mean, yeah, in the 1+1 dimensional models, it's all about that. Yeah, you have some ADS2 here, which is approximately JT. I mean, I didn't describe these calculations here, but there are equations that go with all this in 1+1 dimensions. You can really compute everything, and there's a formula for the page curve that you compute using this nearly ADS2 technology.
Okay, thank you.
There's a question from Devajyoti.
Hi, yeah. So, Daniel, isn't there a way to see this information recovery by calculating like some bulk 2-point correlators, and that they show small, so if there is an information loss, it will decay exponentially, but otherwise at order S time scale, it will show some small fluctuations?
Yeah, so I mean, you can try to study that version of the information problem also. I chose not to talk about that today, but there are some things like that you can talk about, and they seem to work, right? There's this things about the spectral form factor and so on.
So with this island, is it possible to recover that behavior? Has this been done?
I'm not sure. It's that story is kind of okay. There's a word self-averaging that I won't really try to explain, but this page curve calculation has the convenient property that the von Neumann entropy is a pretty robust observable. This page curve is a pretty good thing to compute. These things have to do with tiny little fluctuations they're very theory dependent, that are of order ether minus s, and so to compute them in any robust way, there needs to be some kind of averaging or something that you do. Which complicates the story.
Averaging of what once again?
Well, that's kind of the issue. Averaging of what, right? For example, like you can try to average over the time where you compute the correlator. You can try to average over the theory, right? Which we can debate about to what extent that makes sense. But the story for the page curve is a lot more robust because it's a self-averaging quantity. It's not, this function that goes up and goes down. It doesn't depend on which compactification of string theory you're living in. Whereas the so-called spectral form factor would.
Mm-hmm. I guess I mentioned it because those small fluctuations should still be observable around this page time, I believe.
Well, yeah, page time. Yeah, I mean,
it's not a very late time.
That's a story for a black hole that doesn't evaporate, right? So the things are a little bit different. I mean, but yeah, why don't we not get into that, because that's a whole different version of the information problem, and it comes with its own problems. And maybe in the discussion we can talk about that.
Absolutely. Thanks.
Yeah. It looks like there's one other question from Sundata, but then let's try to go on after that.
Yeah, so I was just wondering, the vacuum energy, for instance, the log p square plus m square integrated over p, that sort of term would give rise to a quartic divergence. Why aren't those sorts of terms considered here?
Well, I don't, yeah, maybe I don't, let me try not to get into that in detail. I'll just say that this generalized entropy is something that's supposed to be finite in the continuum limit. So there are some divergences in G Newton associated to renormalization of the Planck mass. There are divergences in the entropy that are local terms, which are not the one I'm talking about. And those combine to give you a generalized entropy that is scheme independent. But there, yeah, there's a lot more that could be said about that, but let me leave it there.
Okay.
Okay, so all right, so that's it for the quantum extremal surface formula. But okay, great, woohoo, that's awesome. We can compute the page curve. Okay, but what do we really learn from it, right? Why is this formula true? What is it telling us about quantum gravity? So there are two approaches to thinking about the quantum extremal surface formula. I'll begin with the one which is based on Euclidean quantum gravity. So let's first remember what Euclidean gravity says about ordinary black hole entropy, right? So we can also use Euclidean gravity to compute just the entropy of the black hole, never mind these more complicated time-dependent things. And hopefully you all know the algorithm, right? You just, you have this Euclidean Schwarzschild geometry, the thermal circle contracts somewhere in the bulk, and you evaluate the action to find the free energy, and then you differentiate to find the entropy. Okay, so this is what Gibbons and Hawking taught us back in the 70s. More recently, in 2013, this idea was generalized to explain how at least the sort of the first two terms, the up through order g to the 0 in the QS formula, can be derived from Euclidean gravity. And the idea is almost the same as what happened here. It's just that you have to deal with the fact that you no longer have a time translation symmetry here. And so you have to use this replica method to compute the entropy. So the idea is you take the state whose entropy you want to compute, you take n copy, raise it to the nth power and take the trace to give this twisted partition function. So here's some graphical representation of that for n equals 3. And then you analytically continue in n, which you just sort of boldly do, hoping not to get in trouble. And then you take this derivative to find the von Neumann entropy. And so Lukowitz and Maldacena, so this is a sort of boundary prescription for computing the entropy. And then Lukowitz and Maldacena explained how if you kind of fill in these boundary conditions by solving the bulk equations of motion, then what you end up with is the QES formula. It's really, I should say it's not just Lukowitz Maldacena. That was the first, that had the idea, but then to get the quantum correction, there's further work by various authors, Faulkner, Dong, Rangamani. So I should have added more references. It was late last night and I didn't put them all. I apologize. In particular, you can so these Euclidean saddles are qualitatively similar to the Schwarzschild solution. There's some quasi-thermal circle. It contracts, and then you take advantage of the fact that it contracts to find an entropy which is of order 1/g, yeah, it gives you the QES formula. And in particular, you can take this idea and you can apply it to the reservoir of an evaporating black hole, and this confirms that indeed you should have included the island that we had before. Okay, so it's just this Lukowitz-Maldacena idea. You take the Euclidean gravity path integral, and in fact, at the time when Lukowitz and Maldacena wrote the paper, most of us just interpreted this as deriving the RT formula. But their paper was not called derivation of the RT formula, right? It was called generalized gravitational entropy. And they wrote the paper in a way that seemed very annoying to many of us at the time, because they didn't talk about ADS-CFT until the end, right? But actually, their whole point was that this doesn't really rely on details of ADS-CFT. Sort of anytime you have a Euclidean gravity description of what's going on, then this works. And so in particular, like in this case where you have the reservoir coupled to a holographic CFT, the argument goes through just as before and tells you that indeed that you should have included the island. And so that was discussed in these papers a few months after the first papers, after the breakthrough papers. Now, opinions vary, I would say, on how satisfied we should be with this justification of the QES formula based on Euclidean gravity. There's clearly something to it, right? There's some internal coherence that gives you the right answer. But on the other hand, it leaves a lot to the imagination. The basic problem with using Euclidean gravity to compute entropies is that the entropies that you compute are not manifestly equal to the minus trace of rho log rho in some Hilbert space and for some appropriate choice of rho, right? Like if we look at this, the Gibbons-Hawking saddle, right? This is the thermal circle, but then the thermal circle contracts to 0 size, right? But if it contracts, you see that destroys the interpretation of the thermal circle as a trace, right? Does this look like a trace to you? I don't know. To me, it definitely does not look like a trace, you know. And this bothered me for years. It seems there's two kinds of people. There are people who are bothered by this and not bothered by this. People who aren't. I've had trouble convincing the people who aren't bothered by it to be bothered by it, but I'm definitely one of the people who is bothered by it. Okay, it's not a trace. At least it doesn't look like it. But then if it's not a trace, or at least it's not obviously a trace, then why should we believe this answer? Okay. And to say it in a different way, why should low energy effective field theory know the number of microstates in a black hole? Okay. And I can say this just one moment, Sundara. I mean, I could say this more provocatively, right? Like, we think that one of the great successes of string theory is that it's able to count black hole microstates. Okay. But should we take away its credit because Euclidean gravity already knows the answer, right? Who needs string theory, right? We just do Euclidean gravity. It tells us the entropy of a black hole, right? I mean, clearly there's something that string theory did that Euclidean gravity didn't do, right? And I would say what string theory did is it computed the entropy using the formula minus trace of rho log rho, okay? And so to me, that's what it really means to understand an entropy, is to compute it using its definition and not using some other sort of oracle that seems to give the right answer for reasons that we don't necessarily understand, right? I mean, that's why we thought Strominger and Waffe was progress, you know, after Gibbons and Hawking. Okay, Sundara has another question, or no? Okay, the hand is down. Okay, well, maybe I should try to continue because I don't want to go too far over the time. We'll have a discussion at the end. Okay, so this issue of, you know, what exactly does Euclidean gravity mean, right? I think it's very clearly illustrated in 1+1 dimensions, right? So for example, like Jakiv-Teitelbaum gravity is a renormalizable theory of gravity. Here's what it looks like, and actually there are two different ways that you can try to quantize this theory. So the first approach is the sort of textbook one. You just, say study it with two asymptotic boundaries and do canonical quantization, right? So there's a phase space of this theory. It's classical phase space. It's two-dimensional if there are two asymptotic boundaries. I mean, if you quantize this phase space, then you get the quantum mechanics of a particle scattering off an exponential potential. So this was explained by Dan Jeffers and myself back in 2018. So it's very simple, you know, no funny business. On the other hand, you can just say, okay, well, that particle quantum mechanics is boring. Let's try to do something else instead. So let's try to do the Euclidean gravity path integral. So we don't know what it means, right, in terms of a Hilbert space, because we're allowing circles to contract and so on. But let's just do it and see what we get. Okay, so that was the approach of Sod, Schenker, and Stanford. And indeed, right, what you get is that it's not quantum mechanics, right, which is not too surprising. If you take something that's not manifestly quantum mechanics, why should it be quantum mechanics? Okay, in this case, it's actually not. It's some average over quantum systems, basically matrix quantum systems. And so then there's been a lot of follow-up on this over the last few years. And then, so there's this question, okay, like, which of these quantizations is correct, right? I put quantizations in quotes because this one isn't even quantum mechanics, but we'll be charitable to Sod, Schenker, and Stanford and call it quantization. But which of these is correct? So in some sense, both, in some sense, neither, right? So, I mean, both of these are self-consistent mathematical things that you can do. There's nothing wrong with either of these from a mathematical point of view. But on the other hand, neither of these is a quantum theory where S equals A over 4G, right? And my goal for understanding the quantum mechanics of black holes is to have a quantum mechanical description of the situation where S, which is computed using minus trace of rho log rho, is equal to A over 4G. And so somehow this Euclidean approach kind of doesn't really get there. And then here, the canonical approach doesn't either, because in the canonical approach, okay, at least you get something that's quantum mechanics, but it's something that doesn't have any black hole microstates. And so that's kind of boring. The black holes don't really have entropy in this theory. It's kind of, okay. Okay, so that was it for my comments about Euclidean gravity. Let me just see briefly if there are any short questions. If there are big philosophical questions, maybe let's do them at the end. Okay,
maybe I can ask a short question.
Yeah, sure, Sunil.
So you seem to have a critique of Euclidean gravity based on the fact that asymptotically, there's a Euclidean time circle, but in presence of a black hole, it's a contractible cycle. That's so. Does that, in your view, prevent us calculating essentially anything in Euclidean gravity, or is it a specific?
No. So yeah, let me be clear about that. So it's not that I don't like the answers from Euclidean gravity. I think they're actually correct. I just think it's a mystery in some sense why they're correct. It's not something that we understand from the bulk point of view. Because Euclidean gravity is this magic box that lets us know the entropy of a black hole without having to know anything about strings or brains, right? And it's very useful to have a magic box, right? And every time it gives the right answer. So I don't think there's any doubt that it's right, okay? I'm just not satisfied with our current understanding of it.
Okay.
I wrote a paper recently with Edgar Shigulian that I don't have time to get into, where we argued that in some sense, assuming that Euclidean gravity is correct is the same as assuming that the theory emerges from a holographic description. And I think that's really the right idea, is that in any theory that's holographic, Euclidean gravity is correct. But for example, this canonical quantization of JT is not holographic, and so Euclidean gravity is not correct. But that's fine. Yeah, I mean, this theory has other weird features, like it's allowed to have global symmetries, right? Like that's what we were talking about in the paper. So, theories that aren't holographic don't need to have many of the properties we think quantum gravity should have.
Thanks.
I have a naive question.
Yeah.
The circle in front of the cigar, that's supposed to be the boundary of the horizon, right? Is it supposed
no,
to?
No, this is at asymptotic infinity. So the horizon is the tip of the cigar. In Euclidean Schwarzschild geometry over here, that's asymptotic infinity. So this is the asymptotic thermal circle, which is what you want, right? The circle that's the temperature that's dual to the ADM Hamiltonian.
Yeah. So this thermal circle, if you consider it from the boundary point of view, from the field theory point of view, there is no problem, right?
Yeah, but then you're assuming holography, right? Yeah, exactly. So in a holographic theory, this is the thermal circle, and then it's fine, right? Then you don't care that it contracts. I mean, that's kind of the part of this argument that that holography is the real reason why Euclidean gravity is correct. I just emphasize it because people seem to think that Euclidean gravity is a sort of completely satisfactory explanation by itself, and this I don't agree with. But I'm happy to use it as a tool for understanding holographic theories.
So the bulk computation is just the computing the thing over the surface area of the cigar, right?
Well, it's you just compute the action of this geometry. Yeah.
Yeah. So
and then that gives you minus the log of the partition function.
Yeah. So what is the problem with that? Why is it pathological?
Well, because it's not a trace, right? I mean, my understanding of Euclidean path integral is that you derive it from the canonical formulation by, starting with the trace of e to the minus beta h and inserting complete sets of states. And if you follow that rule, you're never going to get a thermal circle that contracts. So this is not doing that, right? Like, and it can't be because it's counting the microstates without knowing what they are. It's amazing, right? Like, when Strominger and Vafa or Ashok or somebody is counting black hole microstates, they're definitely, in string theory, they're definitely not doing this. They have to know the details of string theory for each example they consider.
I thought the trace of the e to the minus beta h was relevant for the field theory, and for the dual gravity theory, it was something else. It was just an action.
I mean, no, we want to compute. That's what we want to compute is the microstates from the gravity point of view. But I think we should go on.
I think we should go on. And Daniel, roughly how far are you away from the conclusion?
I have 23 slides, and right now I'm on slide
just go on then. Yeah.
Yeah. Okay, so I'll try to speed up a little bit. The last part is some new stuff, which probably will be hard to understand in detail anyway. So I'll just try to give a flavor of it. So I would say to really understand the QES formula, and thus the page curve, we would like to compute the entropy of the microscopic theory using the real definition of entropy, not using any funny business, okay? On the other hand, this is hard to do, right? Because then we have to have a non-perturbative description of black hole microstates, right? And so for the non-supersymmetric black holes, which are relevant for the page curve, I mean, we only know how to do this in toy models that, frankly, I mean, I'm one of the authors on these, but they're rather crude. I mean, things like tensor networks, things that throw out a lot of the structure of the bulk that we like, the Einstein action and things like this, right? So one approach, which is sort of in between, which has been helpful for me at least, is that it's possible to reinterpret this quantum extremal surface formula as a feature of, as a really general feature of something called quantum error correcting codes, which gives a rather general way of understanding how bulk quantum information is encoded into the boundary theory in ADS-CFT. So, so in particular, so here's some result back from 2016. So I showed that pretty much any quantum error correcting code obeys a version of the RT formula. I should have written the QES formula here. So here's just a sketch of how it works. So here's a time slice of ADS. I have some boundary subregion capital R. I have its complement capital R bar. And then in the bulk, there's an entanglement wedge of big R called little r, an entanglement wedge of big R bar called little r bar. And then there's this quantum extremal surface sitting in between them. Okay, so this is the bulk picture of what's going on. And so then what I showed in this paper is that for any isometry which maps the Hilbert space of the bulk degrees of freedom in this picture into the microscopic CFT Hilbert space of capital R and capital R bar. So what I showed is that if it has the property that the observables in the entanglement wedge of R are accessible from big R and the observables in R bar are accessible from big R bar, which is some feature of ADS-CFT that you can justify in many cases by using, solving bulk equations of motion and so on. Then this encoding map, or this encoding isometry that maps the bulk Hilbert space into the boundaries Hilbert space has to have this structure that I show on the right. So you take the bulk input in little r, you take the bulk input in big R, you throw in some entangled state between big, and then you hit half of the entangled, you mix half of the entangled state together with little r using some unitary to give you the state here. And then you mix little r bar together with the other half of the entangled state to give you the state here. So this is some theorem. I'm not telling you how to prove the theorem, it's just true. Okay, and so in other words, ADS-CFT is a code that looks like this. This is just how the bulk quantum information gets mapped into the boundary. But you see, as soon as you have this picture on the right, it's clear there's going to be a QES formula. It's essentially obvious, right? Like I take some state rho. This should be a little r bar here. Yeah, it was getting late last night, so sorry, the typos are increasing. This should be little r and little r bar. So I take some bulk state living on this slice here. I conjugate it by this map to push it into a boundary state, rho tilde. And then if in the boundary theory, I compute using the definition of entropy, the entropy of the state rho tilde on this subregion R. Over here, you see immediately what you're going to get. So if I compute an entropy here, the unitary is irrelevant. Okay, so if I compute an entropy here, I just get the sum of the entropy from half of this state chi, and I get the entropy from the bulk degrees of freedom in little r. Okay, that's what I wrote here. But you see, if we define this area to just be this entanglement from chi, then you see this is exactly the QES formula. Okay. Okay, I could say a lot more about that. You could say, is this really the QES formula? Yes, it really is. You can study it in many examples, and this is really the QES formula. So now we'd like to understand this, we'd like to apply this understanding to an evaporating black hole. So that would give us a kind of Hilbert space understanding of this page curve calculation. So here's, sorry, did someone say something?
On the last slide.
The previous slide? Yeah.
So why is that it seems to me the answer depends on the choice of chi, but at the bulk, the RT surface was featureless, right?
Chi is part of the map, right? So chi is not chi is part of the map that tells you how to turn this state of the bulk to the state of the boundary. So yes, that's part of the theory, if you like. So yes, it definitely depends on that.
Bulk, where do I see that freedom? I'm confused.
Well, it's not a freedom. The idea is if you pick a specific example, like n equals 4 super Yang Mills, that will come with a particular UR bar, and chi. Okay. But to figure out what those are, I have to be very, very good at studying n equals 4 on the lattice or something. This theorem just tells you that they have to exist. Okay. So here's a bulk picture for the evaporating black hole. So I'll just kind of a caricature. So we have left moving modes in the interior, we have right moving modes in the interior, and then we have the radiation out here. And so that's the bulk degrees of freedom on this Cauchy slice. Then I want to have some encoding map V that takes these degrees of freedom and maps them into this dual picture where I have the dual CFT S sitting here, and then I have the reservoir R sitting there. Okay. So this is what I said, yeah, left movers, right movers in the reservoir. Just to pad things out, I'll allow for some extra bulk degrees of freedom O that I keep fixed. Like that could be, say, the fields right here, or some fields in between, or something like that. Okay. But for this to work, for when the black hole is old, there's an immediate problem, which is that when the black hole is old, these interior modes, little r over here, and the Hawking radiation, big R over here, are very entangled. And so if you want to have an isometry so you see big R is the same on both sides, but you see if little r, if the entanglement is very large, then the dimensionality of this little r needs to be large compared to the dimensionality of the black hole Hilbert space, which is this S. But then if that's true, there's no way this map V can be an isometry, right? Because isometries can only increase the dimensionality of the Hilbert space, right? But see, R cancels in the dimensionalities on both sides of this, and then little r is here and S is here. So if the dimensionality of little r is already big compared to S, no way this V is going to be an isometry. So the traditional response to this is you say, well, okay, you're taking Hawking's picture of the bulk too seriously. At late times, the radiation isn't really entangled with the black hole. You dummy. Stop trying to do this. Okay, that would be, maybe that's what I would have said to myself, 4 years ago or something. But what we learned from the island calculation actually is that we should take Hawking's picture of the bulk where the radiation and the interior mode are entangled. We should take it at least a little bit seriously at late times, right? Because we use it to find the island. And actually this sort of wrong entanglement between the radiation and the interior mode is crucial for the island calculation to work, right? Like if we didn't have it, then we wouldn't justify including the island, all right? So just in the last few minutes, I'll sketch, and it's only a few slides, I promise, some model that we've recently introduced, which, so this is a real problem. So avoid maybe is the wrong word, that somehow suggests a resolution of this problem, which gives up the requirement that the map from the bulk to the boundary is an isometry. Okay. So that sounds scandalous, right? Like, how can the map from the bulk to the boundary not be an isometry? That's nuts. But actually, in the model, you see that the failure of V to be an isometry can only be seen by measuring very complicated observables. And in this model, actually, it has enough structure to show that this island rule, applied to the wrong state, the one Hawking suggested, that applying the island rule there is actually computes the entropy, which actually is the entropy that you get out of the microscopic computation just by using trace over log rho. So I'll just kind of zip through this. So just to kind of show you, maybe if you just remember a sentence or two from this. So here's what the model looks like. So we have our left and right movers in the black hole. We have some fixed state for this extra, just to pad the Hilbert space dimension. We have the identity map on the radiation, the reservoir, because that's not part of the system. We have some random unitary. And then here's the crazy part. We throw in a final state projection onto some potentially large subsystem, which allows this U to have a dimensionality which is much larger than just the dimensionality of S. Okay. So, maybe that sounds crazy. I'll try to reassure you in a minute, but okay, that's the model. We just have this post-selection at the end. So in this model, then, when we have an evaporating black hole, okay, so here's what the state of the system would look like, right? So we have some entanglement here between the interior outgoing modes and the radiation. This is the Hawking entanglement. I just put it in some state chi2. Then just to keep track of how I made the black hole, I throw in a reference system L that I entangle with the left movers, just so that I can keep track of the microstates of the black hole, how it was made all in one go in one state. And then I just pass this state on this time slice down here through this map to give me a state which now lives in the Hilbert space of the reference system for how the black hole was made, the dual CFT or the black hole microstate degrees of freedom, and the reservoir, which is what I want, right? The microscopic description is supposed to live here. And then the nice thing about this model, you can compute everything. There's nowhere anything can hide. You can figure out what's going on. And so I'll just tell you a few results without giving the derivations, and then we'll be done. So calculations in the model are done by using tools from integrating over random unitary operators. Okay, so if you know that, you know it. If you don't, you don't, but you should learn it. So here are some facts, right? So if I pick two states in the bulk description, and then I take various dimensionalities to be large, then even though V is not in isometry, if I look at the inner product between psi1 and psi2, and then what happens to it after I hit it with V, it's actually very close to being in isometry, okay? When I average over the unitary, because it gives me something that's suppressed like the dimensionality of the final black hole Hilbert space dimension, okay? So if you try to interpret what this says about a fixed generic U, which is what I really want, I don't really want to have an average. I want to pick a fixed U, but just have it be generic. Then what this says is that the map V behaves like an isometry on simple states. Okay, it can't really be an isometry. There are a bunch of states which it annihilates, but it's very hard to find those states. Okay, the states that you get by starting with the Hawking state and acting with a few operators for those states, it will behave like an isometry. And so in particular, simple observables on the radiation will tell you that the radiation is mixed, just as Hawking would have predicted. Okay. But on the other hand, you can compute here it's easier to do the Renyi entropy rather than the von Neumann entropy. You can compute the second Renyi entropy of the radiation. And so here I emphasize you're computing it using the definition, not using the quantum extremal surface formula. And it gives you some page curve that looks like this. So you have a minimum between two things. There's this chi R2, right? That was this entropy of the radiation in the bulk picture. Okay, and so that is one of the options, but then there's another option which starts out big because it has this logarithm of the dimensionality of the black hole Hilbert space. But eventually, if you make the radiation big enough, then actually this term wins, and that's the page curve of the model. And in fact, and I'll just say this, I have one more slide, which I won't explain much. This page curve actually, now the key point is that this also follows by, instead of taking the output of this map and using the definition of the entropy of R, you can also instead apply the quantum extremal surface formula down here in the bulk picture, including this wrong entanglement, and you actually get the same answer. Okay, and that's the main result of this model. And so, okay, sorry, I don't have time to explain the details. I'm running over, but so let me just have one slide to comment on the calculation. So a key ingredient is that my 2016 results were recently generalized just a few months ago by Akers and Pennington. And my version of the QES formula, so in that version, I only gave a prescription of the area of the true QES, not for other surfaces, but to compare to the island story, it's useful to have a more general result that tells you what the area should be also for non-minimal extremal surfaces, because you want to have this story of you have the island or not, and they compete and you see who wins. Okay. And so you need to define the area of the wrong quantum extremal surface. Okay, and so Akers and Pennington give a very nice idea for how to define that. And so in the code we've been discussing, I'll just tell you the answer. This is what their area looks like for the island, where I define the island to be both the union of the left and right movers inside the black hole. Okay, so this is what the area looks like. And then once you have the area, it's easy to plug it into the island, into the quantum extremal surface formula, see what you get, and what you get is exactly this page curve that we computed here from the microscopic description. Okay, so that's all I was going to say. I'll close with just some comments on some open issues, some we're thinking about, some for the future. So what's the relationship of this model to the final state projection of Horwitz and Molesena? It seems to be different, but on the other hand, they both involve a final state projection, so we need to understand that better. How do we think about when the black hole is old, reconstructing the interior operators on the radiation? Is there a connection to the null states of Meroff and Maxfield, who also, for some reason, like to say there are a bunch of states that are annihilated by some quantum gravity map? And of course, we'd like to have a more realistic version of this model. I mean, a random unitary. I mean, come on, right? On the other hand, there's going to be a limit to how well we can do, because we're really keeping track of the non-perturbative quantum gravity description degrees of freedom here. So, doing this for some realistic string compactification seems like a long shot at the moment. And indeed, right, so, at what point are we actually going to need to know about string theory, right? I mean, we didn't use it much in this talk, although we certainly use holography, which I would say is a consequence of string theory in some sense, but shouldn't we have to know it more explicitly? I think we will sooner or later, maybe sooner. All right, that's it. Thank you. Sorry for going over.
Thank you very much, Daniel. A beautiful survey of this field and your work. So yeah, given that it's very late, we should still have a few questions, I guess. Somnath, can you wait a bit and let other people also ask their questions? Then we'll come back to you. Is there anyone else who has a question? Arnab Kundu has a question. Go ahead and ask it. Arnab?
Hi, sorry, I typed in the question, but I
Yeah,
can very quickly ask. So I was curious. Sorry, ignore if you hear any noise, background noise from my end. But I was just curious about the statement that you made. Regarding that Euclidean gravity is meaningful when you have holography. I was just curious. Does that statement make any assumption about the asymptotics of the geometry where you want to have a holographic picture? Or
well, I certainly understand it the best when it's asymptotically ADS. Okay, that's where I would say most of the evidence for this claim comes. Because I don't know what holography in flat space is, right? I mean, if you, I somehow think that in this Euclidean picture, you have this thermal circle that's going off to infinity. I mean, that makes sense also in flat space. And so I guess I would hope that in the holographic dual to flat space, that becomes some thermal circle in the dual description, the BFSS model or something like that, some fancier version of that. But yeah, I'm not sure I can justify it in general, but in ADS, I think we had some pretty solid arguments, which are, relating it to modular invariance and the dual CFT and so on. And yeah, I recommend looking at those. And basically we argued that Euclidean gravity is sort of the minimal thing you can do in the bulk theory to make it consistent with modular invariance. Because why should it matter? If in the boundary point of view, the spatial and the thermal circle are the same, then probably we should. If we certainly we allow the spatial one to contract in the bulk, that's fine. But then probably we better allow the time one to contract too.
But you would agree that, I mean, even if I take it literally, that even in flat space or even let's say in de Sitter, I mean, in some sense, Euclidean gravity throws in answers that are hard to ignore. You might even take that literally, right?
I'm not saying they're wrong, right? It's just that saying that I don't understand something is different from saying that it's wrong, right?
No, I was not trying to say that you were saying it wrong. I was just trying to understand the statement better that you were making.
I mean, there are theories of quantum gravity in flat space where you shouldn't use Euclidean gravity, like the CGHS model, right? That's another one of these renormalizable theories. You can just do canonical quantization. Right? But,
Okay. Thanks a lot.
Chetan, go ahead. You're muted.
Yeah. So I just this last part was a little too quick for me. I probably should read the paper, but
which is not out yet.
Okay, I see. So the general idea is that final state projection together with an explicit trace rho log rho can reproduce the quantum extremal surface calculation. Is that the idea?
That's correct. Yes. Okay. Yeah. I mean, and of course we without the final state projection, in more conventional settings, like where you have a subregion of ADS and you're near the vacuum and so on, then this works without the post selection, right? That was the story from 2016.
Yeah.
Here, right? You see here, there's no post selection, right? But the new ingredient is if you try to make the bulk Hilbert space too big, then this picture runs into trouble, But somehow the and the black hole wants you to make it too big, but somehow even in this situation, the quantum extremal surface calculation is still correct.
Thanks.
Okay, thanks. Okay, Somdat, I think you can be the last to have the last word, and then we will end.
So in the page curve, does it mean that the state starts off as a pure state and ends off as a pure state?
Well, yeah, that's naively what you would expect, right? Like you don't have to make a black hole in a pure state, right? But theoretically, at least, the simplest thing to do is to make it in a pure state. I mean, of course, the astrophysicists would laugh at us for saying that, but we could collapse.
And in the end,
yeah, go ahead.
And in the middle, it's mixed state.
Yeah, the radiation in the middle is a mixed state. Yeah, so I mean that's what this page curve says, right? I mean, and this is not at all surprising. I mean, if you have a piece of coal that's in a pure quantum state and you burn it, right? Like this is also what the entropy of the radiation looks like, right? Where radiation now includes the ash. What I'm concerned is
how can a mixed state evolve to a pure state? Because
because you're looking at a subsystem. No, because you're only looking at part of the system, right? Like so it's the same when you burn the coal. While the coal is burning, some of the coal is still there, and so if you look at the radiation, it's entangled with the coal that's still burning. It's just that once it's done burning, then it has to be pure.
Okay, I think then it may be a good time to close this. If there are no more pressing questions, then on behalf of everyone, let me thank Daniel as well as all the previous speakers of this session. Well, see you all tomorrow. Thank you so much for coming. Thanks for